Last time we were talking about cyclotomic extensions, so let me continue proving a few more facts about these cyclotomic polynomials. So recall we have shown the following. If I take phi n of x, capital phi n of x, to be the product of the primitive nth roots of unity. Okay, so look back on the last lecture for the notation. So these are the primitive gamma n star as the primitive nth roots of unity. We call this the nth cyclotomic polynomial. And what we have shown so far is that this is a monic polynomial with coefficients in z. Okay. Now this time we will establish the following important statement, that in fact this is an irreducible polynomial. In Qx. Okay. So observe, the other thing we know is that the degree of this polynomial is just the value of Euler's torsion function, the number of numbers which are between 1 and n which are relatively prime to n. Okay, so we need to show the irreducibility of this polynomial. So that's our next claim. So the proof is, it involves a few arguments which are reminiscent of what was used to prove Gauss's lemma, which is mostly reduction modulo p. Okay, so let's go ahead and write out the proof. So suppose this is, so if it's not irreducible, suppose we can write it as a product of irreducible factors. So I will write it like this. So suppose not. Okay, suppose it's not irreducible, then I can write it like this. Some product of irreducible factors. The Fi's are all elements of Qx are irreducible. Okay, now recall the little lemma from last time, which was a consequence of Gauss's lemma, which says that if I have three monic polynomials f, g, h in Qx are all monic and f equals gh, then so if f, if f has integer coefficients, then g and h must also have integer coefficients. Okay, so this was a corollary to Gauss's lemma. So we'll use this repeatedly. So by this lemma, what can we conclude? So observe, we have written phi n of x as a product of fk's. The fk's are all irreducible. I can always assume they're all monic. Okay, so now this lemma applies because phi n of x we have already shown to be a monic polynomial with coefficients in z of x. So by the lemma we can conclude the following, that the irreducible factors f1, f2, f3, etc. are all coefficients, are all polynomials with coefficients in z. Okay, so now let me do the following. Let me call this first term. So I have many of these terms. So let me call the first term as something. So I will call this as f of x. So let's call this f of x. Now what does this imply? So let f equals the very first irreducible factor, and let's pick, well, we sort of know what the, let beta be a root of f. So remember, I know what my entire product looks like. Phi n minus x is the product of all the primitive nth roots of unity. Okay, and this I am writing as f1 of x, f2 of x, and so on. So of course the roots of f1 of x will be some subset of the primitive roots. f2 of x will have roots which are, some other subset of gamma n star, and so on. Right? So when you go to the complex numbers, for example, think of them as polynomials over the complex numbers. the roots of f1, f2 and so on are all going to be some subsets of gamma n star. Okay. Now, so I picked one root. So okay, let beta be a root of f. Maybe I should, let me not call this single beta here. So let me just make a more precise claim. Proposition: if beta is a root of f, then beta power p is also a root of f. And what's p? For all primes p which don't divide n. Okay, so that's our claim. So let's prove this. Okay, suppose not. Okay, so observe beta power p is also a primitive nth root. So if beta is a primitive nth root of unity, and p is relatively prime to n, right? So then beta power p is also a primitive nth root of unity, okay? Because the order, so recall what was the nth root of unity definitions, those elements of gamma n whose order is n, okay? So if beta has order n, then I raise beta to a power p which is relatively prime to n, then this also has order n, okay? Okay, so suppose not. So first observe that beta power p is also a primitive nth root of unity. Therefore, if beta power p is not a root of f, then beta power p must be a root of one of the other factors. Then beta power p must be a root of one of these other factors, f2, f3, etc., of one of these, okay. So let me say that polynomial is f2. Okay, so let's say suppose f2 of beta power p is 0. Okay, so let's again call this something. We will keep needing to use it again. So let's just give it a simpler name. Let's call f2 as g. Okay. Okay, so I know the following, that g on beta power p is 0. Okay, what else do I know? I know that beta is the root of f. Okay, and f and g are just the names I gave to the first two factors, f1 and f2. So these are, one guy is called f, the next fellow is called g. Okay, so let's remember all these pieces of notation. Now, what does this mean? So you look at this, f beta is 0, g of beta power p is 0. So therefore, it says that if I form the new polynomial g tilde of x, what is g tilde of x? This is the same as g evaluated at x power p. Okay, this is again some polynomial. In fact, it's a polynomial with coefficients in z. Right? Observe f1 and f2 have coefficients in z, so of course so does g tilde. If I define g tilde in this manner, then observe that g tilde evaluated on beta, which is just g evaluated on beta power p, is 0. Okay, so now I have the following. I know that beta is the root of this irreducible polynomial f, and beta is also the root of another polynomial g tilde. Okay, and f, remember, is irreducible. Okay, so what does this mean? It tells me that f must divide g tilde in q of x. Okay, in fact, by using our lemma, so what does this mean? F divides g tilde in q of x means that, so everything here is over the field qx. This means I can write g tilde of x as f times some quotient u of x. But again, I can use that lemma once again. See, I know that g tilde is again a monic polynomial, f is monic. So of course u is automatically monic. Okay, further I know that this is in z of x, right? Because of course g tilde is just same as I take the polynomial f2 and I put x power p instead of x. So this is in zx, and therefore by that lemma both f and u are automatically in zx. So therefore, I mean, f I already know is in zx, so the only new information is that u of x is in zx. Okay, good. So now this is the equation that I want. I also know that fx is in zx. Okay, so I am going to use this equation. So let's do the following. So this is the key step here. So this is what you also used in the proof of Gauss's lemma. This is reduce modulo p. Okay, what does this mean? This means consider the following ring homomorphism. If I have a polynomial with integer coefficients, I can just reduce each coefficient modulo p. Okay, this is fp of x. So what does it mean if I have summation, say h is a polynomial, hi x power I. Hi is an integer, I just read it modulo p, it becomes hi bar, that's my new coefficient. So that's my map. Okay, that's called the reduction modulo p map, and this map is in fact, and this is a surjective map, this is a ring homomorphism. Okay, as you have seen before. So I can take integer polynomials and convert them into polynomials over the finite field fp. Okay, so now the fact that it's a ring homomorphism means the following. Recall I have this equation here that g tilde is f into u, okay, and all three things are in zx. So I will just apply my homomorphism to this equation. So I have g tilde equals f into u, that's identity, that's true in zx. If I apply my homomorphism, my reduction modulo p to each of these terms, g tilde will go to some polynomial g tilde bar, and f will map to some polynomial f bar, u goes to u bar, and because it's a homomorphism, the same identity holds, that g tilde bar is f bar u bar. Okay, and this is now an identity in the ring fp of x. Okay, so what does that mean? So let's analyze this reduced equation. This just means if I take the polynomial g tilde was just the polynomial g of x power p, and I reduce it modulo p, then that is just going to give me f of x bar u of x bar. Okay, but what is this g of x power p bar? That's the thing we want to understand. Observe, what is g of x power p? The whole bar means so let's say g looks like some gi x power I, then first I have to replace x by x power p. So I'm saying, suppose gx is the polynomial gi x power I, then I first plug in x power p, and then I do bar of this, right, which means I just take summation gi bar x I p. Okay, and this is a polynomial fp of x. But recall this is the reason for reducing modulo that same prime p, and that p and this p are the same. This is a calculation which we have done many times. If you have a field of characteristic p, then when you want to raise this to the power p, then what you get? Well, you just get the same coefficient, so it's this power p. So recall that if I computed this quantity, then that would just be gi bar power p x to the ip, but gi bar is in the, so this is because the characteristic is p, the field has characteristic p, but further gi bars come from my finite field fp, and in my finite field fp, this is because gi bars come from fp. If I raise an element to the pth power, I just get back itself. Okay, so that's the important observation here. So finally we conclude that this quantity here is nothing but you take g of x bar, that's the thing that's inside here, and you raise it to the p. Okay, so g of x power p bar is the same as g bar x whole power p. Okay, that's a strange identity, but that comes about because the character, I mean, you are going modulo the same prime p here somehow. Okay, so now we are ready to complete the proof. So what do we get? So we have g of x, I take gx bar whole power p is the same as f bar of x u bar of x. Okay, it's an identity which holds in fp of x. But what does that mean? It means that, you know, f bar and g bar must have a common factor. So this means, well, okay, let's establish that properly, the following. So let's do the following. Let's just take an irreducible factor of f bar. So let some polynomial v bar be an irreducible factor of f bar. Okay, then what do we know? Therefore v bar divides the right hand side, therefore v bar divides the left hand side of this equation. This is just g bar whole power p. Okay, but if an irreducible factor, so v bar is irreducible or it's prime in that ring, you know, it's in fp of x over the field fp. If v bar divides some power of a polynomial, then since v bar is reducible, v bar has to divide that polynomial itself, since v bar is irreducible. Okay, so what does that mean? Therefore v bar is common to both f bar and g bar. So therefore v bar divides f bar, that was our assumption, and v bar must also divide g bar. Okay, so that's really what we were after. Now let's go back and see what f and g were. Okay, we have managed to get a common factor. So this was our original phi n of x, right? So I called this as f. This was my second factor was g. Now what I have sort of concluded is that f and g, they have a common factor. Okay, so it seems like f and g have a common factor. That was my v bar, but this common factor is after reduction modulo p. Okay, it's not as they are, but only after reduction modulo p. But that's still good enough. Okay, so let's reduce everything modulo p and show that this is a contradiction. So now let's go back and recall, where are we? This is f, g, and then maybe there are other factors. Okay, but now let's reduce both sides modulo p. So I'll take this x to n minus 1. Think of it as reduced modulo p, the coefficients, which means it's really again x to the n minus 1, but in the so this is just, you know, when I reduce the coefficients modulo p, I just get back 1 again, but I have to think of these as now being 1s in fp. This is f bar of x into g bar of x into some other terms, but f bar and g bar have one common factor, which is v bar. So there is definitely v bar inside f bar, there is another v bar inside g bar, then there will be some additional factors in f and some additional factors in g, and then there were these other additional factors. Okay, so I don't care about all those. So I have many more factors maybe, but what I care about is that the right hand side has v bar squared followed by some other polynomials. Okay. Now, why is that a contradiction? Well, observe that the left hand side is the polynomial x to the n minus 1 in fp of x. So this is now an identity in fp. This is v bar squared into other terms. This means that the left hand side has a repeated root, right? Because this is v bar squared, right? So this means that x to the n minus 1 has a repeated root in some extension. So it's not a separable polynomial. i.e. x to the n minus 1 thought of as an element of fpx is not separable. Why is that? Because there is a v bar square on the right hand side. So if you go to some extension in which v bar has a root, then that root will occur twice on the right hand side. Okay, But this is a contradiction. Why? Because we can easily check that x to the n minus 1 is separable. This is a contradiction since x to the n minus 1 is separable in fpx. Well, how do we check it? Remember, we have the derivative criterion. Okay, let's check. So I just take this polynomial, let's call it h of x, x to the n minus 1. What's its derivative? H prime or dh? Well, it's just n x to the n minus 1, and observe that p was chosen to be not dividing n. So nx to the n minus 1 is not 0 here. Okay, because p doesn't divide n, therefore n times something is not 0 in the field fp. Okay, and observe that h and h prime do not have any common factor, have no common factors. In other words, their GCD is 1. Why is that? Because the only factors of h prime are powers of x themselves, right? I mean, it's just x power something. So the only thing that can possibly divide h prime is some power of x, but powers of x don't divide h, right? So this has only 0 as a root, and that definitely doesn't have 0 as a root. So that's the contradiction. Okay, so that contradiction establishes the following claim. So therefore our claim is established, our claim is proved. What was our claim? Well, our claim was the following, that if beta is, so if some primitive root of unity, nth root is, if this is a root of f, then so is any power, then so is beta power p for all p primes not dividing n. Okay, now so that was our claim really. Now it proves this claim. Now from here one can conclude that in fact every primitive root of unity must be a root of f. So from this we make a further claim. This means that every gamma in gamma n star is a root of f. Okay, and well, that's rather straightforward, because all you have to do is observe that from this claim that we have just shown, this says that, you know, if beta is a root, then beta power p for any prime p not dividing n is a root, but beta power p is a root, so that power another prime is a root, and so on. So this is a root implies this is a root. Now you keep iterating this. This tells you that anything of this form, beta power p1, p2, pk is a root, provided the p's don't divide n. Take primes which don't divide n, and of course you can repeat the primes. So I can say p1 to the m1, p2 to the m2. So each of these is a root of f. Okay, and this is for all mi's greater than or equal to 0. Okay, so I'm just iterating my earlier claim. So what does that mean? In particular, it means, see, look at these numbers on top. What are these? These are exactly how you construct, this is exactly how you construct numbers which are relatively prime to n, right? So those are just going to be powers, products of, you know, prime powers where the primes don't divide n. So this means that beta power r is a root for all integers r which are relatively prime to n. So for all r such that the GCD of r and n is 1. Okay, but then recall that's exactly how you get every element of gamma n star. So this means that every element gamma in gamma n star is a root of f. Okay, so what does that mean? It means that our original equation x to the, sorry, this was phi n of x Okay, we had, this was the full product of x minus gammas, gamma and star. This was f of x into g of x into, you know, other terms and so on. But what we have just proved is that all these roots are all roots of f of x itself, okay, which means that none of these other factors could have existed, right? Everything is already a root of f of x. Therefore, it means that, and remember, f was irreducible, it was the first irreducible factor. Therefore, we have shown what we claimed, that phi n x is f, and therefore is irreducible. Okay.